So we found out that feature engineering can be done. We found out adjacency and the incident matrices can provide us node edge connectivity. Then the question is why we need to learn features automatically or in a different way. So look at some of the challenges associated with feature engineering, particularly by using the classical concepts, or I would call it by hands. It is possible that whatever features we have chosen may not be optimal for downstream tasks such as node classification or graph classification, because we have used features without taking into account downstream task. Finding an optimal engineered feature is a difficult task and we have to go through trial and error. Now the question is, can we do automatically? Or we can develop algorithms which allows us to do feature engineering automatically, which is I call feature learning or learning of features. Feature learning allows us to automatically learn features given the data or given a graphs or node features, etc. It also allows us to take into account downstream tasks, and downstream task can guide the feature engineering or learning of the features. So we can actively involve downstream tasks like node classification or graph classification or link prediction to find out what are the optimal features for particular applications. And it also provides optimally learned features for a specific task. Hence, it is possible that for a node classification, certain features might be better than the graph classification, and feature learning and representation allows us to do that. And that's why we are going to move towards feature learning rather than feature engineering. The embedding is one of the way of doing the feature learning. So what is embedding? It's a representation. Okay, it's automatically learning the features. It translates the high dimensional vectors to a lower dimensional vector space, or take a matrix and create a vector out of it. It provides a compressed numerical representation, of course based on certain optimality criteria, but it provides us a good representation of data or graphs. Also, we can use certain criteria to get a meaningful representation. For example, similar inputs are embedded close together. Similar kind of graph structures are embedded in a similar manner. Okay. One of the main advantages, or some of the main advantages of embedding or learning features are it eliminates sparsity. Other main advantage here is we can actually use different models for the same embedding. We can actually decouple the task of learning the features from using it for predicting certain labels. In that case, the embedding can be invariant to the model used later on for prediction applications. So we can use or reuse same embedding again and again for different models if we have actually done done a good job in learning embedding all the features. And also, of course, it is efficient for the computations because embedding can be done separately. We'll see in some of the applications why it is efficient later on. But these are the main advantages of embeddings. Take a simple embedding here. So I have done embedding here, which actually is using some algorithm which leads to 6x2 matrices. Dimensional array is reduced. Here each row represents particular node. So it is U, V, W, X, Y, Z. And each column represent some lower dimensional space in which this embedding is taken place. Now, once we have embedding, what kind of different embedding we can do? So, there is a graph representation levels. Here we can actually do embedding for using each node characteristic, or we can actually do embedding for take a graph. Each node has a different embedding or representation, and once we have that, we can actually use that representation for variety of tasks involving the nodes. It can be node classification, link predictions, community detections, but the embedding remains same, and after that we can actually use them for different purposes. So, that is one way of we can use graph representation for node embedding. Other two are subgraph embedding level representation. So, I will take a set of nodes together and use their embedding, and this can be used for clustering similar node or finding out new nodes role in a graph or a subgraph. So, here I have taken a 3 subgraph node as a subgraph, this as another subgraph, and for each of them I have a embedding. And then new node comes, we can see whether they should go to this subgraph or other subgraph. Another classical application, which is a graph level task, where each of this graph is going to be a different graph, and for each of them we will have a embedding. So, for each graph I have one embedding. Remember molecular property prediction task, in that each molecule is a graph here, and for each of them I have embedding, and then I can do graph level representation for different application, for relationship between graphs, or for finding out, given a graph, what is a property of that particular graph. So, what we can do with the representation and embedding is the question. So, representation is basically allows us to represent the graph as a vector. It can be possible as a complete graph as a vector, or each node in the graph as a vector. In this case, I have represented each node as in a graph as a vector, and we'll show or we'll see in some of the tasks when we talk about graph neural networks that this task is will be followed by certain other function which provides us a feature for a graph, but for a while we'll look at only nodes as embedding, and once we have node as embedding, we can use this representation to perform classification, regression, or clustering tasks using different kind of models. Here, the representation learning allows us to decouple task of feature engineering from the model, and the advantage here is then we can use the existing models like logistic regression, decision tree, neural networks, etc., to perform node level tasks or graph level tasks. Hence, whole idea of graph as a data is divided into two parts. First, learning the graph representation, and then using the existing model for performing downstream tasks like classification, regression, and clustering. So, next couple of lectures we look at how to go from the graph to representations. Thank you.